right, so we're going to continue with chapter 25. This is going to include continental drift. It will include talking about, start with that. Plate tectonics is really just like a theory describing the Earth's crust being composed of plates that are kind of floating on the Earth's mantle, and they move around. So this creates a situation where the land masses move, and basically the continents are going to move. So you can see this image here shows the plates and where they are located. You can see along these, where these red dots are going to be areas where there's like a overlap of some of the plates, which results in some earthquakes. Now, the land masses of Earth formed supercontinents at least 3 different times during its most recent one is called Pangea. Right, so this happened about 250 million years ago, and the effects of forming a supercontinent are pretty significant on the organisms that existed at that time. So what happened was, when this one continent formed, it deepened the ocean basins over here, but then also reduced the shallow water habitat, because there is one large, if you think about it, there, both of these cases, this one large landmass would create deeper basins over on the opposite end of the landmass, and then along the edges of the landmass is where the shallow water habitats are. However, when there's one large landmass, it reduces the surface area of the land, which again is going to reduce the shallow water habitats. And then in the middle of this continent is going to be a lot colder and drier because it's not near the water. So if you got this one large piece of land, it's quite cold, and in most cases, many organisms would likely not survive when that happened. Now, the movements of the plates on the mantle cause them to create this continental drift. So you can see here the progression of the change in the Earth's surface, or at least the continents on Earth, over time. So here we have the supercontinent, and then they're starting to separate here. This is the present day continents, and so on and so forth. Now, organisms have risen and fallen over the course of time, and this results in different speciation and extinction rates. So, the organisms that existed on Earth really depend on these rates, the rates of speciation and extinction. Continental drift has had effects on the organisms, and I told you why when we were talking about the Pangea and the effects of creating that supercontinent. When continents move, organisms have to adapt to a new environment, and or move to an area where they can survive, or of course become extinct. Now, the distribution of fossils and living groups reflects the movement of the continents. So we've identified fossils in parts of South America that are similar with fossils that were in Africa. So this kind of solidifies the thought that this large landmass did actually occur around the time that those fossils were dated, which is about 250 million years ago. Now we're going to talk about mass extinctions and how they can affect organisms. The fossil record has shown that many species that have ever lived, actually most species that have ever lived, are now extinct. Extinction can be caused by changes to the species, and this could be due to biotic or the abiotic environment. So the biotic environment perhaps would be other organisms, perhaps loss of food source, or an increase in the predators, or abiotic environment, which would be basically let's say the environment became a lot colder, or let's say became desert-like, so again, lost some of the biotic resources. Now, at times, the rate of extinction has increased dramatically, and that usually. Let's look at this graph right here. This is a really interesting graph. There is what's called the Big Five in terms of mass extinction. Now, there's been several mass extinctions, but there's really 5 major mass extinctions. Now, each of these 5 of the Big Five mass extinctions resulted in at least 50% or more of the marine species becoming extinct. Now, we can see here, we've got one right here, and then another, and then here, and then here, and then here. Oops, here. Now, the extinction rates tend to increase when the temperatures are high, but that's not always the case. So if we look at this graph right here, we have the relative extinction rate of the marine animals again, and this is when it's cooler, and this is when it's warmer. So going up the graph would indicate more extinction events, and going to the right would be in the warmer climates. So up in the right, top right quadrant of this, you would expect to see more mass extinctions. And you do. However, there is a mass extinction when it was cooler here, and then there are several extinction events, probably a little bit more extinction events that occur when the climate is cooler than it is warmer, but they would be considered mass extinctions. Now, looking at this graph right here, you can see that mass extinctions can result in a sudden decrease in species, but then immediately after, often there's a huge increase in new species that arise. So here we've got the percent of predator genera along with the time, and you can see where there are a couple mass extinctions that are kind of highlighted. So if we look at this right here, we have a significant decrease during this Permian mass extinction, but immediately after there's an increase in predators, or basically new species that can arise. And then they gradually decrease, and then, just maintain constant, and then we have the Cretaceous mass extinction, and then a sudden increase in predators immediately after. Now, mass extinctions can also, they can eliminate lineages that have these really cool, novel features that are typically advantageous. However, the mass extinction isn't a form of selection against this this feature, this advantageous feature. One example would be the shell drilling gastropods. So they can drill holes into shells. Think about what benefit that might provide the gastropods. What do you think? Well, I'm thinking if they can drill holes into the gastropods, these very strong shells, it would provide a way for them to obtain a food source. Well, they became extinct at the end of the Triassic and didn't appear for 120 million years. Now, that just tells us something, right? So some things can become extinct, but then they can appear. However, it may be millions of years later. Adaptive radiation is the term that's used for that very large increase in new species that arise after mass extinctions. Adaptive radiation ultimately is an increase or rapid evolution of diverse species from a common ancestor, right? This often happens after a sudden decrease in species. Because adaptive radiation kind of depends on new environments and depends on the fact that after a mass extinction, there's a lot less competition because a lot of predators have been extinct due to this, whatever event occurred to cause the mass extinction. And of course, loss of some major predators could occur as well. So if we look at this graph right here, we have the Big Five in yellow. Right? So we can see the big five in yellow. And of course, you're going to see a decrease in species right where those arrows are. And then there are other mass extinction or other extinction events which aren't really part of the big five. But you can see immediately after each of these big five or any other major extinction event, you can see a sudden increase in species. So here you've got the decrease right there, and then you have a sudden increase, which would be the adaptive radiation, right? So we have the extinction event causes a new environment, and the reduction in competition and predators, which could result in the explosion of new species. And then this continually happens, and it's seen whenever there's a mass extinction. Mammals are a good example. They underwent an adaptive radiation after the dinosaurs became extinct. You can imagine, it kind of makes sense, right? The dinosaurs were major predators of mammals and many other organisms. Once the dinosaurs became extinct, the mammals got to diversify, and this caused quite an increase in the number of species of mammals over some time. Now, this can have the last one was overall, right? So all over the world, but there can be just regional adaptive radiations, which are just kind of locally concentrated, right? So one example would be on the Hawaiian Islands, right? Each of the Hawaiian Islands are basically a different environment. So there's what's called the Silver Sword Alliance. It's a diverse group of plants that descended from a ancestral tarweed, which started out in one of the islands, but then, once they began to grow within the other environments, other characteristics were selected for, even though they're related, but they were different species. They originated from the same ancestral species of tarweeds. You can see they're quite diverse in structure, and some of them are can only exist on certain islands. Some islands may have more than one species. Well, as a concluding this segment, just to remember that continental drift and mass extinctions have had great effects on organisms, making major organisms become extinct and then allowing other organisms or new organisms to radiate or diversify after the mass extinctions.